Thank you. All right, let's get started then while everyone's here. So my name's Jamie Coleman. I am a software developer and advocate for IBM. So I generally work around the Java ecosystem and containerizing and modernizing people's infrastructure. And today I wanted to talk to you a little bit about some of the research I've done on JVMs, because as a developer, I don't get to touch JVMs as much as I'd like. I use them all the time, but knowing the in and outs of them and how they work and what you can actually do to them has been not something. So let me just share my screen and we can get started. All right. So hopefully presentation now. So like I mentioned, the topic today is we're going to be talking about simple tweaks to get the most out of it. And like I mentioned, my name is Jamie Coleman. I'm a developer advocate and engineer for IBM. I had a bit of a weird story. I started off working on mainframes, so very different technology to kind of runtimes and Java runtimes and stuff, and then moved on to the WebSphere team where I was on their container team. Then I worked on some DevOps kind of stuff, and then became a developer advocate. So getting to play around with all this cool tech, proving that it works and showing you guys. So let's get started. So what we're going to be talking about today. So these are some of the things we're going to be talking about. First of all, what is the JVM and why is it important? How the cloud has changed how we use JVMs and what we expect of them. Then I'll use today, so Hotspot, OpenJ9 or GraalVM. Then looking a little bit about different runtimes you use on your JVM, and then some tweaks you can do to your JVM and what you should be doing as an engineer or a Java developer with your JVM to get the most out of it. Then hopefully I will be able to give you a demo if the demo gods approve today. And then we'll talk a little bit about some of the different things OpenJ9 offers. And now some of these things are available in other runtimes. So I know Hotspot provides JIT server, etc., and things like that. So you can take these technologies and use them on different JVMs. Then we'll talk a little bit about a technology which fascinates me, which is starting to be worked on by different teams around the world. So hopefully it'll come to fruition soon. And then just a little bit of a recap at the end. Okay, so let's begin with, why is the JVM important? Well, we wouldn't have Java without it. So kind of what does it do? Well, the Java virtual machine language. So your computer can actually do something with it. So most other languages compile for specific systems, but Java compiles for kind of the Java virtual machine, and this can be run on any kind of system, hence the phrase write once and run anywhere. So why do people use JVMs? Well, again, like I mentioned, cross-platform, you can generally run Java anywhere. It's got a large library ecosystem. People have been using Java for a very long time, over 25 years. So as you can imagine, the library ecosystem is quite huge. So there's libraries pretty much for anything in Java these days. It's got a great on that from the developer and lets the JVM handle all of it. It's got some powerful monitoring tools. It's been around for, again, a long time. So people have created some great monitoring tools for it. And it's proven and robust. Now, it has been the dominant programming language for a very long time, and that is because it's been used time and time again. It's very robust. It's very secure. So it's really a good kind of, Java is a great language to use, and it still is and probably will be for the foreseeable future. And we know it's robust because it has been used for over 25 years now. Full overview of the JVM architecture. Again, I'm not a Java JVM developer. I don't work on JVMs. But just so you've got a bit of an idea of how they work, you generally have 3 different subsystems. You've got the class loader subsystem, the runtime data area, and then kind of the execution area. So a little overview, diving a little bit deeper into there. So the class loader subsystem generally performs things like loading, linking, and initialization of our class files. So obviously the loading part loads 3 different class loaders. You've got Bootstrap extension and the application class loader. Linking basically verifies bytecode and prepares all the static variables. And then initialization kind of assigns static variables to their original values and then executes the static block. So the variable stores metadata and code for your methods, etc. You have your heap, which is the common memory shared between different threads, and that stores stuff like objects, instance variables, and arrays. Then you've got the JVM language stacks, and this is created when a thread is created and stores local variables. The PC register, and every time a thread is created, it has its own register, and this stores the address of the Java virtual machine instruction, which is currently executing. And then finally, the native method stack holds. So onto the execution side, bytecode and executes it using the interpreter and the JIT compiler. So how are these different? Well, the interpreter interprets the bytecode faster, but executes it a lot slower. So the disadvantage of using the interpreter is when one method is called multiple times, every time a new interpreter is required. Whereas the JIT compiler neutralizes the disadvantages of this, and essentially the execution engine will be using the help of the interpreter in converting bytecode, but when it finds repeated code, it uses the JIT compiler, which compiles the entire bytecode changes and changes it into native code. So this is a lot faster than the interpreter, but the interpreter, yeah, it's not always thread safe, so sometimes, yeah, the JIT compiler is used. The native method interface interacts with native method libraries, and last but not least, the native method libraries is just a collection of native libraries. So that's kind of a very, very small overview of what a JVM is and how it works. So how has this changed over the years? Well, nowadays, we are moving more and more things to the cloud. These resources aren't our own, they are rented. So something I want you all to kind of take away from this is don't always think about, resources in terms of money. That money also corresponds directly to energy. So now we're running this stuff on the cloud. We do need to think also about the energy we're using. Because these data centers, they're using a lot of the world's energy. And as developers, we're kind of responsible for trying to reduce that. So if you can imagine what the cloud offers, and this is a local data center, so the dark blue is what we need, the resources we need, and the light blue is the resources that we have, but we're not using, as you can see, for 1/3 of the time. Now, that's wasted resources for us because we've had to buy those resources to handle that peak load, but most of the time we're not using them. So this is just energy or resources that are just sitting there in our data center. Now the cloud's come along, which is great, and it allows us to then share those resources with other people. Again, I'm trying to phrase this in terms of saving energy and resources rather than the money aspect of things. But now we're freeing up those resources for other people around the world to use. But now if we move to like microservice architecture or function as a service kind of architecture, we have more granular control over our applications and our services. So we can now basically buy smaller compute units and then free up more of the resources on the cloud and free up more energy for other people to use. So microservices are great, but they've changed the way things work. So it's great when you have one or two of them, but now we're running lots and lots of microservices. And I think the problem that a lot of people get to with Java is we kind of have the overhead of a JVM. That JVM has to sit in every one of our microservices. And yeah, we're basically running a JVM for each microservice. Whereas, say, 15 years ago, before containers and microservices, we would have lots of applications running on one JVM. Whereas now we're not. It's really a one-to-one ratio when you're looking at microservices. So what does that mean for JVMs? Well, JVMs aren't the same that they were 10 years ago because they've had to basically change the metrics and balance their performance in different ways. So now really what we're looking at is CPU usage, startup time, footprint, ramp up time, response time. Now, of course, making changes to these characteristics in a JVM may have detrimental side effects on other characteristics. So finding a balance is quite difficult. And that's something that we really need to do because, again, we have this overhead of a JVM in every one of our microservices. So looking at old technology here, Java Me inside, this was one of the greatest phones ever, but it had very, very similar requirements. So looking at it, we had small footprint, fast startup, and quick immediate ramp up. Now, it was a bit different back then. It wasn't the case of we were trying to save money on resources. These phones didn't have the resources to have, massive, massive applications running and big JVMs, etc. So that's kind of what the same requirements that we have with the JVM in the cloud: small footprint, fast startup, quick immediate ramp up time. So trying to get back to where we were constrained by the amount of resources we could have, as opposed to we're not so much constrained by the resources now, just the money or the energy we want to save. So why should developers care about optimization of our applications? It works well, it works well enough for the customer, and it doesn't actually save that much money making these little changes. But when you put it into a bigger perspective, so think about it like this: there's over 500,000 data centers worldwide. They consume a massive amount of area, so the same size as 6,000 football pitches. And these stats were from a couple of years ago, so it's probably higher than this now. But for example, data centers, and they're these buildings that everyone's using every day, using their mobile devices, etc. They are currently consuming, and this was in 2019, the same as the UK's energy supply times 1.5. That's a lot of energy being sucked into these warehouses that we can't see, and most of society has no idea exists. So yeah, for us as developers, we need to really stop. We really need to focus on making our code and make our applications performant. So looking at it, so hardware engineers have been really doing the bulk of the work here in making sure we don't drain the world's resources on energy. That because of hardware efficiency, they have managed to flatten this curve. And as you can see by this graph, if they carried on with the same trends that we had in 2010, so hardware didn't get any more efficient from 2010 onwards, it stayed the same, we would be using a hell of a lot of energy to power these this infrastructure in these data centers. But for us now, as it's time for us to focus a bit on our code and a bit on the things we're doing to help flatten that curve, but even hopefully make that curve go down eventually. So there are loads of different JVMs. It's one of the great things I love about Java and the JVM is there is pretty much a JVM to do anything. As you can see, there's one even called Wonka JVM and Squawk, and yeah. So there's some JVMs to do everything, whether it's running on Arduino or Raspberry Pis. So kind of Internet of Things to JVMs, all the way up to kind of enterprise grade stuff. There's also one on here, the Maxine JVM, which I'll talk a little bit about later. But that's kind of what GraalVM is based on today. But I'll talk a little bit about that when I get to it. So these are the most popular JVMs that you see out there. So you've got Oracle JDK, obviously the different Open JDKs, including stuff like Amazon and Microsoft JVM, and then Azure and Graal, and then of course you've got Eclipse Open J9. This was originally IBM's JVM, which they open sourced, I think, about 4 years ago now. So let's talk about 3 of the most popular ones that are out there that are used by lots of different people. So the Hotspot JVM, a bit of a background here. Sorry. It was released in 1999, and this became the default Sun JVM, which is now Oracle. And in 2006, the Hotspot JVM and the Java development kit became open source. And this was amazing. This basically paved the way for all the different flavors of JVMs we have out there in the open source community. So why was it called Hotspot? So Hotspot continuously analyzes the program's performance for hotspots, which are executed often or repeatedly. And these are then targeted for optimization, leading to high performance execution, which basically that's where the word hotspot kind of comes from. So that a little bit of an overview there of Hotspot. OpenJ9, so this has been IBM's Java for a very long time. It was open sourced, like I said, about 4 or 5 years ago. It can be a very small JVM, or it can go for very large, depending on what your requirements are. So if you're using it in microservices, it can be very small. Or if you're doing it in a more old-fashioned way, where you're deploying it to a virtual machine with lots of different applications running on the same JVM, then it can go to large. And again, because it's been IBM's JVM and it's been at the core of our some of our Java products, it has been used by lots of the biggest enterprises on the planet. So it is a very robust JVM. So they about, say, 5, maybe a bit longer years ago, OpenJ9 team kind of went to the drawing board and said, we need to create something that's a bit more performant, a bit more cloud native. So they have really been chasing these amazing stats that they're getting today. So for example, 51% faster startup time than Hotspot. Again, similar things with footprint. When you talk about ramp time, well, where you're waiting for your JVM to ramp up, that is really wasted resources. So we want to kind of get to where it should be as quick as possible. And we don't want it to, when it's under load, start expanding and requiring more resources. We want it to be able able to cope with that. So OpenJ9 is really great for some of these kind of cloud native characteristics. So GraalVM, this was originally released. This is quite a new. I'm not sure I call it a JVM, but it's a bit different. But what is it? So it's released in May 2019, so very well, quite recently. It's based on the Hotspot OpenJDK with roots from, like I mentioned, the Maxine virtual machine, and this was developed by the University of Manchester in the UK. It was developed quite a few years ago, and at the time there wasn't so much need for kind of a JVM with these kind of characteristics. And well, with the rise of containers and microservices, etc., that's completely changed. So I presume basically they looked back at that project and thought, okay, this is actually quite useful. So it has a new JIT compiler for Java, a new Java compiler. It allows ahead of time compilation, which is great. So you can run it with the GraalVM native image. It also employs truffle language implementation frameworks, and so the GraalVM SDK will enable different programming language runtimes, which is awesome. And it also works with LLVM and JavaScript runtime, so a bit different to normal JVMs. Now, these were the goals of the GraalVM project. And this is kind of, they have to kind of go back to the drawing boards with this. So to improve the performance of Java virtual machine-based languages to match native languages, to reduce the startup time of JVM applications, so using stuff like compiling ahead of time, to enable GraalVM integration into Oracle database, etc., to allow the freedom of mixing code from different languages, so polyglot applications, and to include an easily extendable set of polyglot programming tools. Now, there are benefits of using native compilation, like some of these here, but there are drawbacks as well. I think throughput and a few other things can be things that can be drawbacks. So it does really depend on what your application is doing, what your project is doing, and your goals. So some of these things can now be achieved with not using native languages. So it's all kind of, yeah, you do have to weigh up the advantages and disadvantages, but you'll find all this information online, and yeah, you can make your own decision. So it's all well and good, you know, we get the right JVM for what we're doing, but if we're using a runtime that is, you know, not for what the goal of our kind of application or our project, then it's basically going to just be wasted effort. So picking different runtimes is very important. So I'm going to go through OpenLiberty first. So this is the main thing that I advocate for. This is an open source runtime provided by IBM. It came out of what used to be WebSphere, but essentially we wanted to go back to the drawing board and create a runtime that was developer friendly and was more cloud native. So these are some of the characteristics and what of the goals that we had when we were creating this runtime. So just enough, so not too big. We wanted it to be really easy to code, so using stuff like dev mode and supporting the right tools and the right frameworks, and also zero migration, because we want, you know, we want users of our products and our technologies to take the latest innovations. You know, there's 250 developers working to make new functionality and features, but if everyone's on a version from 2 or 3 years ago, then yeah, you're really not getting the latest and greatest stuff. So zero migration is key, because it means someone could move from an old version to a new version, and hopefully, well, that's the hope. Their code should not break, and they shouldn't have to redo any of it. And again, onto the cloud ready side, stuff like it was, well, that's the second job I did at IBM after I worked on mainframes, was to containerize OpenLiberty. Again, it's just like small disk footprint, efficient memory usage. The throughput is amazing. So for example, if I compare the throughput of OpenLiberty to, say, with Spring compared to, say, Tomcat, that you nearly got double the throughput. So hopefully that would mean you need half the services and half the resources on the cloud. And it has a self-tuned thread pool, so as a developer, you don't have to worry about any of that. So like I mentioned, it's just enough for application server. It's very, very small, and you add in the features and the functionality you want depending on what your application is doing. We've generally been the first to certify in a lot of different things. So as you can see, Java EE8, we were the first to certify. Jakarta EE8 and Jakarta EE9, we were the first to certify. And for a lot of the different micro-profile levels as well, versions, we were also the first to deliver working code for that, which is awesome. So I can't not mention Quarkus. This is a runtime provided by Red Hat, and it has very similar goals to OpenLiberty. Unified configuration, so kind of put all your configuration in one place rather than having to configure loads of different things. So same kind of concept of OpenLiberty. Zero config and live reload. So that's kind of what dev mode does. So the ability for you to change some code and that code automatically be deployed rather than you have to restart servers, etc. And it's got native execution. So this Quarkus allows you to use things like GraalVM to do native execution to allow you to get those really, really fast startup times. And this is why GraalVM is really cool, because for functions as a service where you need it to come up, do a function and shut down very, very, very quickly, that's when the native execution stuff really shows how good it is. But if you were having really long running applications, then yeah, there's trade-offs. And again, it supports loads of libraries, so Spring, MicroProfile, Jakarta, stuff like that. So yeah, a little bit. So as you can see, just from here, the startup time with Graal and Quarkus is ridiculously fast. So if you are doing stuff as function as a service and you really need that capability and that matters a lot, then yeah, this is a really, really good runtime. Now, there are lots of different runtimes. So again, different runtimes have different characteristics. So pick the runtime that's for you and that makes sense, depending on what you're doing. Okay, so tweaking the JVM. So kind of what this talk is about a little bit. So first of all, you're responsible as a developer. We need to write efficient code. So that is the first thing that I would say it needs to be done if you want to get the most out of your JVM. Use the right JVM for your needs, which I've talked about already. Pick a runtime that's right for your application, which I've talked about already. Use profiling. So profiling is amazing. To look into exactly what your JVM is doing. I've never really played around with it. Again, I'm not a JVM developer, but when I started doing the research here, I started playing around with it, and what it shows you is quite amazing. Pretty much everything that's going on inside your JVM. And tweak your JVM. So different JVMs, like I said, have different functionality and different features that allow you to tweak it and get the most out of it. So these might differ depending on your needs. So in development, you might do something different to what you're doing in production. But no matter where you are, really, get the most out of your JVM. Even like, for example, class cache sharing, which I'm going to talk about later, even enabling that made, for example, my IDE start up quicker. So there are lots of things you can do, even if it's just subtle things on your local machine. Okay, so writing efficient code. So first of all, using primitives use primitives where possible, because this will improve the performance of your application. Use string builder rather than string buffer. It's more efficient, but it's not string. Which one is it? String buffer is not thread safe. So bear in mind, if you need thread safe stuff, then use string builder. But string buffer is generally more efficient. So if you can, use that. Avoid using iterators where possible, and also things like avoid using big integer and big decimal. If you don't need a big integer and you don't need a big decimal, there's no point of using them because it'll just consume more of your memory. So try and use the variables or whatever that are right for your needs, as opposed to ones that you're never ever going to use and you're just using that just to cover all kind of edge cases, or make the edge cases so big that it's not really an edge case. So like I said, use the right JVMs for your need. Not only are, there's lots of different JVMs, but there's lots of different types of JVMs, flavors of different ones. So you'll have ones in containers that are built on like ARM images, etc. So really have a look at the JVM you want to use, and then look at the different flavors of that JVM to see if there's anything more that JVM offers that you can use, especially when you're using things like containers, and it's very easy to base on top of different images. So back to picking the right runtime for you. So for example, if I look at this, Webs for Application Server and things like JBoss were great application servers, but they're really not built for this microservice world. And I'll explain what I consider a microservice in a minute. OpenLiberty is great because it pretty much has all the capabilities of Webs for Application Server, but has really fast scaling, really high memory throughput, very small memory usage. So OpenLiberty really fits really well across the different scopes. And then if you move to Quarkus, it's really great for things as like functions as a service. So like, again, being able to start up and shut down very, very quickly. And for things like microservices using things like Spring and MicroProfile. Now, what I consider a macro service is it's not a distributed monolith. That is what I would consider a well-built monolith. A macro service is kind of this state I find people getting into when they're trying to break apart older applications into microservices. And then sometimes you kind of realize, okay, some of these services or some of these things are so highly coupled that breaking them apart would require so much rewriting of our code that it just doesn't make sense to. So then you end up with kind of bigger services, but they generally contain more than one kind of function or one kind of service. But they make sense to scale those services at the same time because they're all related to one another. So it's kind of an in-between, I find, between monolith and microservices that people end up getting to when they're trying to break apart monoliths. Profiling. So like I mentioned, profiling is awesome. It's something I've only just recently started using. Essentially, they're tools that enable you to monitor your Java bytecode constructs and operations inside your JVM. Looking at things like garbage collection, object creation, method executions, iterative executions, and thread executions. Now, when you start looking at this stuff, yes, it's a lot of information being bombarded at you, but after you start reading and through it, you can actually follow where your code is going. And if you write a very simple bit of code and just execute a line, it's very cool to see where it's going and what it's doing in the JVM. So there's lots of different profilers you can use. JProfiler is one, YourKit is another, Java Visual VM is another, NetBeans profiler, or if you've got the Oracle JDK and you can use the Oracle Java Mission Control. When I was playing around with it, I just used JProfiler. That seemed to work very well for me. So yeah, it's entirely up to you which one you use. They all do very, very similar things. Okay, so tweaking your JVM. So first of all, you can tune your garbage collector to be more efficient. That I would definitely say is worth doing. You could use stuff like the at-in-time compiler. This is enabled on lots of different JVMs. Basically, yeah, it compiles your code ahead of time. Enable class data sharing, and I will hopefully provide you a demo with this later. This is available on JVMs like the Hotspot or OpenJ9 JVM, but this can really help start up your applications a lot quicker than if you just use your JVM without tuning this. Idle tuning is good. So basically, when your JVM is not doing anything, it can save a bit of resources and then idle, so go down a little bit. If you're paying for a certain amount of resources, that won't help you, but it will help save energy around the world. So having this enabled is good. The JIT server is really great. It allows you to basically create some extra servers to offload kind of computing and compiling that JVM's doing. And by doing that, it enables you to handle constrained environments. So if you constrain an environment a lot, basically it can help keep that running. And start with a minimum heap size. Now, not too small because it'll make sure it'll probably break your application, but try and find a comfortable one. And as you're developing your application, increase it as you need it. Because generally we always start with a heap size which is too big, and we don't ever change it. I've never really changed my heap size. But starting with a smaller one and slowly increasing it can help. And also, again, when we're using just one application or one microservice for the JVM, every little tweak we do, because we could be using hundreds of these JVMs, and will save us kind of resources and energy when we're running in the cloud or even in your local data center. So OpenJ9 class data sharing, and this basically enables you to start up your applications a lot quicker. So what is this? Essentially, it's basically a shared bit of memory of a fixed size that persists beyond the lifetime of a JVM and a reboot. So you can create as many as you want. You just give them essentially a different name when you create their shared class cache. So this is just a JVM option we pass in. It can't grow in size, so it is a fixed size, but you can change the size of it if you want. And it's limited generally by the underlying operating system. So how does it work? Well, normally with a JVM, the kind of lookup order or the class loader order would be your class loader cache, your parent, and your file system. Whereas in contrast with this technology enabled, it's your class loader, your parent, then your shared class cache, and then your file system. And what it basically is doing is all the classes you're using on startup, and you're using them pretty much every time, rather than looking through the file system for those classes, it puts them in this shared class cache, so they're available instantly for the JVM to find, as opposed to having to look through the whole file system. So it's very easy to get started with this. Like I said, it's just a JVM option. I'm going to show you how to pass that in very simply with OpenLiberty, and hopefully we'll see a difference in startup times. But yeah, it's just a case of adding the X share classes. And then if you want to give it a name, that enables you to basically create different caches for different applications, etc., but all on the same JVM. And again, you can specify the cache size simply by adding the parameter. So comparison. So the OpenLiberty, as you can see here, is starting up in just over 2 seconds. And So we're comparing it to some other runtimes here. This is without using the shared class cache. If we enable it, OpenLiberty drops by nearly just over a second. But it's not just OpenLiberty. If you look at all the other runtimes, they have all gained some kind of startup benefit here. So regardless of if you use this with OpenLiberty or not, you could use this for any runtime and you will get benefits of using this technology. And again, it's the same kind of with Docker. So in Docker, this is enabled by default, which is great. And even then, we're getting a startup time of OpenLiberty of just over 2 seconds, as opposed to 6.5 that it was before. Now, OpenLiberty is reaping the benefits of this technology a little bit more because a lot of work has gone into OpenLiberty to really kind of get the benefits of this, and some work has gone into OpenJ9 to make it more performant, etc. Right, so now I'm going to show you a little demo. Let's see what time. Okay, we've got 10 minutes, so hopefully I can get through this demo quick enough. So we're going to get started quite simply. All we're going to do is basically, I'm just going to find a sample application we can use. So let's say we'll create the REST one. Hopefully you can all see my screen. So I'm just going to clone this down locally into my repo. And in here, we have a finished directory, the basic finished application in. So we're going to, of this demo, let me just open VS Code. There we go. Okay, so it's a very simple application. What we're going to do is start Liberty up. So simple command, Liberty. Perhaps if I can spell today. Run. So while that's running, it's going to download its dependencies, etc. I'll leave that there. What we're going to do is I'm just going to, if I go into main, there's a folder here, Liberty config. Server XML is basically the file used to configure the OpenLiberty server, but we're going to create one called jvm.options. So what this is going to do is when OpenLiberty starts up, it will pass this file into the JVM, so these options are then added. So the option we need is x share classes. Yep. So that's all you need. Again, you can give it a name if you want to. I'm not going to give it a name on here because I'm only using one application, etc. Okay, so we'll just wait for the application server to start up. Once it's started up, it should give us a time of startup. I'm presuming probably, I don't know, 5 seconds or something like that. How the shared class cache works is you've got to remember that the first time we run it with this option, so I'm going to shut that down. It's got to populate the shared class cache because it doesn't really know what kind of classes I'm using first time. So let me just go back to my code. Yeah, I'll save that. So that's all saved now. So the first time I run this, again, it's got to populate the shared class cache. So we might see a bit of a decrease in startup time, but not the startup time we're going to be looking for. And then I'll run it again afterwards. And then hopefully, according to the demo gods, we should notice the startup time decrease dramatically, which is what we're looking for here. And so the message I'm trying to get, it was especially with something like this, which is also available on Hotspot. So that was 3 seconds. So that was impressive. So now I've enabled it again. Let's see if we can get that down even more. But again, yeah, so a lot of people are using Hotspot, a lot of people use OpenJ9, and it's a very simple thing to enable. Now, imagine if we enable this on all our microservices and all our applications around the world, how much money and energy we could save by getting our stuff to a little bit quicker. And again, the whole point of this is I just want to show you how simple and easy it was just to add this in. Okay, so we've got start time is 2, and then check to see essentially if to check and also to see if any of the classes I'm using can then be added to this shared class cache. So yeah, just a very simple thing to show you how to get your startup time down of your applications just by adding a very simple JVM property. And again, this technology is available on Hotspot. I've not tried it on Hotspot, but I do use it on OpenJ9. And if you're using it, you can also use this JVM if you're using stuff like Eclipse, etc. It will also enable your IDE, your Eclipse IDE, to start up a lot quicker. But as you can see, I'm not actually using Eclipse. I'm using VS Code. So yeah. So yes, time of 2.3 seconds. So again, it's to basically start up even quicker. Okay, so I'm going to go back to my presentation. Okay. we finished off here. Okay. So idle tuning, I mentioned this very briefly before. Essentially, this allows you to save some resources when basically your JVM is not doing anything. So for example, if you can see here, this is with idle tuning turned on. And as you can see, when there is no load, basically it will try and save some resources. Now, if you're paying for a certain size, like of hardware and resources, etc., it might not save you any money, but it will save some energy around the world. So it's like turning your lights off. When you're not in the room, turn your lights off. That's essentially what this JVM is doing here. And for OpenJ9, this is the default setting in containers. So if you pull this down as a container, you're already getting the benefits. So the JIT server is quite cool. Basically allows the orchestrator kind of allows for load balancing and stuff, but it basically allows different kind of JIT compilers to be run in different places. And what does this enable? So this kind of enables better throughput. So we have OpenJ9 as one, and then OpenJ9 with the JIT server running. And when they've got basically all the resources they need, they're fine. But as you can see, as we constrain the environment more and more, so we take a bit of memory away, the throughput of normal OpenJ9 JVM is starting to slow down a bit. And then if we constrain it by a little bit more, as you can see, it's really dropped dramatically. Whereas with the JIT compiler, as you can see, that throughput is still, it's dropped a little bit, yes, but it's still, handling what it needs to do, which means at least our customers aren't going to get horrible errors. At least, it might take a few seconds longer for them to basically get their request done, by which time hopefully your scaling systems will have kicked in and hopefully scaled up to the point where it won't be a problem. But in the meantime, if it takes you 1 second or 2 seconds or a bit longer to scale an application, then you're going to have to wait. So basically having it really cope with that constrained environment allows you or your orchestration system, whatever it is, Kubernetes or OpenShift, to allow it to scale up quicker. Well, not quicker, allow it to scale up so your customers, essentially aren't getting their requests received. So very simple to enable. Just in one command line, you just essentially enable the JITs. You basically a client mode, so it basically sends this to the JIT server, and then another one, you just start the JIT server process. So very simple to get started with. Okay, how long have we got? Got about 3 minutes. Okay, should be able to cover the rest. So is there any future tech to the rescue? Well, this is something that I think is awesome. I've been looking at it for about a year, and it's now really starting to get looked at as a serious kind of technology. So cryo is what we call it. The real name is checkpoint restoring user space, and its potential for reducing startup time of applications. So you won't have to move all your stuff into native code. You can use your code how it is, but essentially it's kind of like a restore point. This has been a feature of the Linux operating system for a while, so it enables snapshot or a checkpoint to be taken of a running application. So this technology will hopefully enable us to start up even quicker. So this is without it enabled. So with an application, a runtime that takes just over 1 second is now down to like 0.2 seconds. But you really get the benefit of this technology when you're looking at applications that have big startup times, because that's where you really see the difference with this. Now, there are challenges with this technology. There's lack of encryption on the snapshots, which is being addressed. No address-based layout randomization, which can be a bit annoying, but again, being addressed. Predictable random number generators, but there are libraries or different number generators you can use to get around this. Running as a non-root user in containers, because a lot of people don't want to run as a basically run as root in the container, so finding a way around that. And there's also no API to kind of specify when the snapshot should be taken. So it's really up to the different runtimes and the different people implementing this to kind of create these APIs so that it knows the right time of your build or your deployment to actually take this snapshot. But it is a very promising technology, so do keep your eyes out for something for this coming along in the future. So I think we're basically at the end of time here. I've got about 1 minute left. So just a quick recap. Hopefully you've learned something today. If you want any clarification on some of the stuff I've talked about, do reach out to me. My Twitter and some of my contact information will be on the last slide. The main things I want you to really take away is as Java developers and engineers, we need to write efficient code. That is the real #1 to get the most out of your JVM and the most out of your application. Use the right JVM for your needs. There's no point, trying to write this efficient code if you're using this humongous JVM sitting in lots and lots of different microservices. So really pick the right JVM. Same with runtimes. There's no point, trying to create these super efficient code on this super efficient tweak JVM when you're using, a runtime that's like 7 GB in size, or takes like, 5 minutes to start up or a minute to start up. So that is obviously another big thing. And then profiling, just have a play around with it. If you've never actually dived into the internals of your JVM, very easy to set up something like JProfiler. So do check it out and see what some of your code does as it travels around. And of course, tweaking your JVM. So like I've mentioned, using stuff like idle tuning, using JIT compilers, using like class cache sharing, hopefully Cryo in the future, using all this stuff and taking advantage of these new JVM technologies will hopefully not only save you or your organization money, but it will save energy around the world. And I think I'm probably right in saying that there's probably more Java applications running around the world than any other kind of different language applications. So if we make all these tweaks to our applications, hopefully we can start making a small dent in the amount of energy we're using in these humongous data centers and in our private data centers. So here's some links to some of the materials and some of the things I've talked about today. So feel free to have a look at those. And again, I'm not an expert on JVMs. This is something that I was quite intrigued about, something that I use JVMs all the time being a Java developer. So I did look around the internet for lots of this information. So there's some links here to some of the research and some of the information I got today. And with that, I think I have come to an end. I'm about 40 seconds over. Again, do reach out to me. My email address is there, or reach me on Twitter. But yeah, if you have any extra questions about any of this stuff, please do reach out and I'll be more than happy to answer them.